Good morning, everyone. I hope you can hear me okay. I'm sorry I can't be with you to present this lesson in person, but I'm hoping this video will help you understand some of the things in this topic. So today we're starting to learn about water quality. The essential question for this topic is whose responsibility is it to keep the water clean? Obviously, we all have access to some form of water. In Cambodia, it's through our tap or through the Mekong River. But eventually all that water ends up in the ocean, and all the oceans are connected. So whose responsibility is it to keep that ocean clean? Okay, because if we dirty it in Cambodia, it's going to dirty the ocean for the rest of the world. Does that mean it's our responsibility to keep it clean? Should other countries have to clean up after our mess? Or what? So as we're going through learning about water quality, keep that in the back of your mind. So just a few things about this video. Going on Google Classroom, you'll see that there is this question up there. It's just titled video questions for Monday's class. Everyone will need to complete one of these. So if you are listening to this video with your friends, so you're sharing earphones or something like that, you still need to turn in your own questions. Okay, everyone needs to submit something by the end of class. I will indicate on the slide and through the audio when you need to answer the question. Please make sure you pause the video at those points, answer the question, and then go back to the video. Do not change your answers if you get them wrong. It's okay. Alright? I'd rather see you get an answer wrong than just get the answer that I wrote 5 seconds after I asked the question. Okay? So what you will need to do is write down the number as well. So for example, this is question 1. You just put a little 1 next to it. I'll go through an example the first time it comes up. Okay, so firstly, we have a whole bunch of water on Earth. Okay, if we took it all, we'd have, this little ball here. We talked about this last time. That's the amount of water, but the amount of fresh water is this tiny little ball there. So the first question I want you to answer, question 1 is, what makes this water here? So what makes this water not fresh? Okay, I'd like you to just write a short list, let's say 3 things. 3 things that make this water not fresh. So what you should do is go on to Google Classroom, okay, put a little 1 down there, okay, just like it's indicated. And then answer that question, what makes this water not fresh? Okay, just pause the video, answer that, and I'll see you shortly. Okay, so sorry for that long wait. Hopefully you've written your answers there, and I'll have a look through them later on. One of the main things that you should have all written, the easiest one, would have been salt. Okay, salt is the biggest thing that makes that water not fresh. There's other things such as the fish excrement, all that entails. There may be some other pollutants in there, like chemical pollutants from factories or oil from oil spills, but salt is one of the main things that makes this water not fresh. Today's class, we're going to look at a process called desalination. Okay, we'll look at more about what that word means later on, but we're going to look at why desalination is important. Okay, especially in terms of not having enough fresh water. We're going to look at some terms about how we can talk about the other things in water that are besides water. Then we'll look at how we can do some simple calculations relating to salinity and concentration. Okay, so firstly, pure and non-pure water. Hopefully you guys remember that water can be described as 1 oxygen and 2 hydrogens. So our Mickey Mouse ears. Okay, also known as H2O. So allow me to cheat for a minute, and I'm going to represent a water particle or a water molecule as that green blob. So in pure water, this should hopefully be revision, but in pure water, all we have are molecules of water. Okay, I'm drawing mine a bit too regularly. They should be a bit more scattered around and a bit funny looking, but we only have water in a sample of pure water. In non-pure water, it's like H2O plus. Okay, it's H2O plus a whole bunch of other things. So if I have my cup of water again, I have a similar thing to before. I have a whole bunch of water in there. In fact, most of the molecules in this cup are going to be water molecules. But if there is even one particle or one molecule that is not water, there's something here. So it is automatically non-pure water. Pure water only contains water molecules, only contains H2O. If there's anything else in it, it is automatically non-pure water. So as soon as you introduce a little bit of salt, okay, that could be salt right there. As soon as you introduce a little bit of sugar, a little bit of, oil or whatever it is, that automatically makes the water not pure. Now, you may say, or you may realize, that makes it really difficult to find pure water. Okay, because as soon as you add anything else into it, a little bit of dirt, it's not pure. Pure water is not the same as fresh water. So it is not the same as fresh. Fresh water is more like pure water, okay, than non-pure water, but there's still a bunch of other stuff in it. Okay, we don't have to drink only pure water. In fact, a lot of the water that we drink has a lot of good minerals in it, okay, that are good for us. So when we want to talk about how pure or how fresh water is, we can use this term concentration. When we talk about concentration, all we're doing is we are measuring the amount of a dissolved substance. So that is just the non-water. Okay, so that could be your salt, it could be your sugar, it could be ketchup, I don't know, it could be anything else inside that water. But it's the measure of the amount of that stuff in a particular volume of solution. So that solution, what we mean by that is your water plus whatever else is in there. Okay, so a solution could be, let me just wipe this. A solution could be your tea, if you drink tea. The solution will be your, I will say cordial, you would call it syrup. Okay, that sweet drink that you have, that is also a solution. Anything that is water plus something else, we can call a solution. So we can look at how much of your other stuff is in that water, in that solution. We can measure that in a percentage of mass or in grams per liter. So all we're doing is we're saying, here's a bunch of water. I'm going to use the blue this time. So this is all water molecules. All we're trying to do when we talk about concentration is we're trying to measure how many other things. Okay, we want to measure how many of this other stuff there is compared to all of our water. If we have something with many non-water particles, non-water molecules, we'd say we have a high concentration. If we have one with very, very few, we have a low concentration. So let's take a look at these calculations and see if we can be able to do, if we can look at doing these calculations to figure out percentage mass. So a can of Coke has a mass of 368 grams. Let's highlight that for later. And it contains 38 grams of sugar. Calculate the concentration of sugar in percent. So, two things we need to know. We need to know the mass of the dissolved substance. Dissolved substance. And in this case, we're looking at the sugar. And so that's going to be 39 grams. Next thing we need to know is the mass of the solution, because we need to know how much the total thing weighs, or how much its mass is, and that is 368 grams. From here, you just need to do a percentage calculation, and hopefully guys you remember how to do that. So I'll write out a formula for it. So percentage equals mass of dissolved, so mass of dissolved substance over the mass of solution, that's my way of writing solution, times 100 to get your percent. Okay, sorry, those look like 66s, 100. So if we jump up here, let's write that out. 39 divided by 368 times 100. And on my calculator, if I punch that in, 39 divided by 368 times 100 will give me 10.60%. Okay, that means in any 100 grams of Coke, so in any 100 grams, you will have 10.6 grams of sugar. Okay, so that's a way of saying concentration. You'd say the concentration is 10.6% sugar. Alright, so when you pick up a can of Coke, 10% of what you're feeling is sugar. Right, this is question 2. So in video questions down here, you should write 2 and then write the answers to these questions. Okay, you don't need to show your working out, just write in the number. Feel free to rewind this video and come back to go through the working out. Pause the video here and I'll see you in a second with your answers to these 2 questions. Okay, so let's go through these answers. 35 grams of jelly in 200 grams of water. Okay, so this is your dissolved substance. This is your, write that out. Dissolved. This is your solution times 100. So 35 divided by 200 times 100 will give you 17.5%. Sorry, that looks like a 12. 17.5%. Okay, down here, bubble tea, the mass of our dissolved substance is 45 grams. The mass of our drink, of our solution, is 500. Times it all by 100, and you should get 500. You should get 9%. Okay, so in your drink, 9% of that mass you're feeling is the powder. The next way we can talk about concentration is in grams per liter. This is a measurement of the exact same thing. Okay, we're still measuring how many particles of your dissolved substance there are to the amount of your solution. It's just that in this case, instead of looking at the mass of your solution, we're looking at the volume of the solution. Okay, remember, mass is how many particles there are. Okay, so you could say there are, 8, 9 particles here, 10, whatever. Volume is looking at how much space they take. So they reflect the same thing, they're just 2 different ways of indicating it. Okay? In our course, you'll see that if I give you a volume of solution, you'll probably need to calculate concentration in grams per liter. Okay, because volume works with grams per liter. So let's do this. can of Coke has a volume of 355 mils and contains 39 grams of sugar. Calculate the concentration of sugar in grams per litre. Remember, guys, if you have that formula, you should be able to figure out, if you have that unit, you should have a little bit of an idea of what formula we'll need to do to get that. That's not something you have to know, but you may be able to figure it out. So, what we need to do is have mass. So let's change my color here. Let's go with black. No, blue. We need to have the mass of your dissolved divided by the volume. Sorry, this should be in grams, by the way, for the top. Divided by the volume of solution. And note, this has to be in liters. Okay, please make sure you convert your volumes into liters. So this is in milliliters. So from mils to get to liters, you need to divide by 1,000. Okay. So let's do that. So we have 39 grams divided by 355. Okay, but before I put that in there, I need to do 355 divided by 1,000. What that'll do is, if we have a decimal point, 355.0, okay, so let's divide by 1,000. So 1, 2, 3. That's where my new decimal point goes. So 355 becomes 0.355. Okay, that's in liters times 100 again for percentage. Oops, sorry, didn't write that at the top. Oh no, I don't need to do percentage. Apologies. Sorry, I got confused there. So that will give you, let me do my calculation, 39 divided by 0.355 gives me 109.86 grams per litre. Okay, it means that in any litre of Coke, 110-ish grams of that litre, 110 grams in that litre is Coca-Cola. Is sugar. Alright? So, rewatch this if you need to, so if you can figure out how to do that calculation. Then I'd like you to try answering these in number 3. So please write a number 3 in your Google Classroom question, and then have a go at answering these 2 questions, and I'll see you in a couple of seconds with the solutions. Okay, pause the video. Alright, let's go through the answers. So, first one, some people like to add types of salt crystals to their bath water. You have a 200 litre, so that's the volume, bathtub, and you're going to add 20 grams, so that's your dissolved substance of crystals. So we need to do 20 divided by 200. No, this is in litres this time, so it's perfectly fine to use it as is. And that will give you 0.1 gram per litre. So in 1 litre of your bath water, you'll have 0.1 gram or 0.1 grams of the crystal. That same drink of bubble tea below has a volume of 475. Okay, so that I think was 550 gram drink has a volume of 475 litres. In that, you still have that 45 grams of powder. What's the concentration? Well, it'll be 45 divided by 475. Okay, 45 grams divided by 0.475 litres will give me 94.74 grams per litre. Okay, so if you had 1 whole litre of drink, you would have 94.74 grams of your powder. If you are still not sure about that, maybe scroll the video back a little bit and have another watch, and then try these questions again. Okay, so that was for figuring out concentration. There was 2 ways of giving concentration. What we're going to look at now is a particular type of concentration. That's called salinity. Now, salinity, you might guess, relates to salt. Okay? If we're giving a concentration of salt, okay, that's the salt that you eat, that type of salt in water, we can also call that concentration salinity. So this is still a type of concentration. It's just a special case. Okay? Ocean water has a salinity of about 4%. So that's our percentage mass, which means 4 grams in 100 grams of ocean water. Sorry, this water here refers to ocean water, not pure water. So what I'd like you to do is, if 100 grams of ocean water has 4 grams of salt, how many grams of salt would there be in 1 kilogram of ocean water? Okay, just pause the video, write in your answer, and I'll see you in just a sec. Okay, hopefully what you've got is, well, we have 10 times as much water. Okay, because from here to there, you have to times it by 10. So our 4 grams here, we need to times by 10 as well. Because we have 10 times as much water, we'll have 10 times as much salt. So we will have, I'll write down here, 40 grams of salt in 1 kilogram of ocean water. Okay, so that's about a teaspoon of salt in 1 kilo of ocean water. What that means is that salt is more dense than fresh water. Remember that density, is a measure of grams per mil. So how much mass the matter has divided by how much space it takes up. Why that is because, let's say these are my water particles, my water molecules, sorry. Okay, pure water or fresh water, let's say pure water. Pure water is only water molecules. Okay, so its volume is that, okay, whatever that much is. If we add salt into that, salt doesn't stack on top. Okay, it doesn't displace my water. What happens is that salt is going to fit in between the already existing water molecules. So you'll notice the volume is not increasing much. In actual fact, it would increase a little bit, but nowhere near as much as if I was just adding salt on top. What this means is we now have more particles in here. Okay, so mass has increased a lot, but volume has not. Okay, we still have this cap at the same amount. Okay, like I said, it will actually go up a little bit, but not that much. So what this means is we have more grams per mil, so density will increase. And as we learned in our last unit, that means that salt water has a greater buoyant force, meaning that you can float higher or easier in salt water than you can in fresh water. Okay, 2 questions to answer here. Please stop the video and answer these 2. Again, I don't mind if you get them wrong, but just make sure you think about them. Take a minute, maybe chat with the person next to you, and then answer. Well, how is fresh water made in the water cycle? So at what point does it actually become fresh from salt water? And what happens to the salt that was in the water? Okay, so what happens to that now? Stop the video, and then we'll move on. Okay, so let's first look at where we have salt water. You guys know that the rain is pretty much pure water. Okay, it may pick up some pollutants on the way down, but it at least starts off pure. Here is where it kind of starts to get less pure, okay, or less fresh as it goes through the ground, as it goes in rivers. It starts to pick up, salts. It starts to wear down some rock, grabs all of that stuff, and by the time it gets into the ocean, it is very much salty. But during the process of evaporation, which takes heat energy, remember, we need the sun to power this. Okay, without the sun, we have no evaporation. So during this process of evaporation, only water, so this is pure water that is evaporated, goes up into the clouds. And what happens to the salt that's left behind, sorry, what happens to the salt is it's left behind. Okay, so we have all that salt that was in this water here is being left in the ocean. So why don't the oceans become more salty? Well, that's because at the same time, more water, less salty water is coming in from the rain. Okay, so the cycle continues, and the amount or the salinity of ocean water remains relatively similar. Okay, but you may say that, if we continued, if we maximized evaporation and stopped rainwater from going back in the ocean, yes, our oceans would get more salty over time. Okay, if their volume decreased, they would become more salty. Anyway, that was off topic. So, what that was is a natural example of desalination. Desalination is just, the opposite of salination. It's any process that takes out the salt from water. And what you should end up with is pure water and a pure or solid salt. So, if this is my ocean water, that's the pure water, here's the salt. What we want to end up with is pure water in one container. So 1, 2, 3, 4, 5, 6, and my solid salt in another container. That is desalination. In the water cycle, it required evaporation. Okay, evaporation to first get the pure water removed from the salt, and then condensation to turn the water vapor, okay, because it's a gas after it's evaporated, to turn that back into liquid water. So we need evaporation and condensation. And where does that energy come from in the natural water cycle? Well, it comes from the sun. Okay, so if we wanted, let me skip back. If we wanted to do desalination, okay, because we need more fresh water. More people means more people need to drink water. We want them to drink good, clean, fresh water, not polluted water or salty water. Okay, you can't drink that. What we need to do is have a way to get the energy. Okay, so we could use the sun. Okay, and that's what some places do. They have, well, the sun already exists, but they have big, shallow pools of water. Okay, and they can use that to get rid of, to collect the water. Okay, so that will evaporate, and they can somehow recollect it. Or we could have geothermal. Okay, where we use the heat rising from the earth. Okay, to cause evaporation of water, which we can then collect. Okay, condensation, we can collect it, or we can use, I forgot the other one. Anyway, those are two things we can use to power desalination, but it takes a lot of energy. Okay, imagine if you had to boil all of the water into gas and then recollect it. Okay, it's going to take a whole lot of energy. What I should mention here is to condense something, you need to cool it down. Cool. It does not mean you need to make it cold. You just have to make it below 100 degrees. 100 degrees Celsius, and it'll cool. So what I mean by this drawing is, if you make the water, so think about it on your stove top. Okay, you can have fire here, or a hot plate. You have some water. As it becomes hot, it boils, and you get vapor forming. If you put a plate or anything above that, when the vapor hits it, it's going to cool down a little bit, and then it's going to start condensing, and it's going to flow. And if you put a cup here, okay, you will collect this water as it drips off, okay, and that will be pure or purer water than you started with, and all the salt you had left will be left behind there. Okay, so what I mean by solar and geothermal powering it is we're using that for the source of heat. So let's put your knowledge to the test. This is a hypothetical situation. You are stranded on a deserted island. There is plenty of water, but it is all salt water. It does not rain on this island, so you cannot just wait for rain and collect that. You have a bucket, a piece of plastic. It can be like a large, a meter by meter piece of plastic, and a small cup, as well as a lot of sand, rocks, and trees. Your final question, number 7. How can you make fresh water from all of this salt water around you? I'll not give you the answer to this one today. We'll look at it in our next class. But think about it. Take 3 or 4 minutes and write out your explanation. Please do not look it up. I want this to be from your thinking, not from Google. Okay? Alright, once you're done with that, okay, please submit that question, okay, and check Google Classroom or ask your teacher for the next task. Thank you guys for listening. If you have any questions from this video, please first just have a quick flick through your textbook. The answer may be in there. But if you can't find it, just send me a quick email or write a comment on this post and I'll do my best to answer it. Thank you.